All right, good morning, folks. Good to have you back. Really appreciate you all coming in today. I've got pretty much full house. And if you haven't dropped your name in the chat yet, please do so for attendance purposes. I've got lots of stuff in the chat. Looks like most people have already. So that is great. Thank you for doing that. Today, we are starting Unit 1048, our semi-automated and automated welding unit. In this unit, we focus more on gas metal arc welding and that process. We touched on some other things like MIG welding, or not MIG welding, submerged arc welding, stuff like that. A little bit on flux core as well. But our main focus is gas metal arc welding. And in the 20 level, we start to explore flux core more. So you always say that, Junior, every single time. I think you need to turn up your volume unless everyone else is having problems. Maybe you just have poor audio output or pickup on your device. Can anyone else hear me? Is everyone else okay? Throw something in the chat.
I can hear you.
You can hear me? Okay, awesome. Thank you. Cool. So that is that one. Yeah, maybe your device, Junior. You've mentioned that a few times and people have said that they're able to hear me. So let's maybe explore that option a little bit. Maybe some headphones might help if you're in a space that's a little noisier. But I'll try and speak direct and nice and clear to the computer so we can have a good audio for the session. If noise persists in the background, I'll throw on a microphone and we'll record that way. But what we're going to do today is we're going to start up our FAB 1048 unit. We're going to learn about the basics of gas metal arc welding, the principles of the machine, and just how the operation works. And I've got a slideshow for that. So today's class, we're going to narrate over the slideshow for you. We're going to record this whole lesson, and that will be in the online classes for your reference shortly after this class is complete. And there will be some quizzes going forward. There'll be some worksheets, some online stuff. I'm going to give you the basics of what I need to. I'm not going to give you any fluff, but enough to get the point across so you can demonstrate concepts and show me understanding when you get back into the class. All right, so I'm going to share my, okay, yeah, no, that's fine. There will be a recording and he can look at that recording when it's posted for the class. So I will start sharing my screen now and we will get this going. So we're gonna go to Brightspace. What I've done is in our semi-auto welding unit now, I'm gonna switch to student view so you can see what it's gonna look like from your perspective. So when you flick into your semi-auto unit, you're gonna see this. Just like normal, we're gonna go to resources and then down to content. From there, we're going to see gas metal arc welding. That's the unit we're going to work in. And we have our 1048 gas metal arc welding PowerPoint. So this is student view. So this is exactly how you would see it. You can pop it out here. And then you can open with Google Slides. And then what I do is I always present from there. You guys have access to this. I've given you all access to it. And this is how I show it for you guys. If you're ever looking at a slideshow and you want to see it just how we do it in class, it's going to be done just like that. So gas metal arc welding equipment, unit 1048. It's awesome. I love gas metal arc welding. It's a neat process. It's not a new process. It's been around for a while, probably since about 1924. A gentleman named Alexander patented it in about 1924. So pretty neat. Oh, there's the patent drawing. So what we have here is a lot of very, very similar components to today's modern gas metal arc welding setup. It's taken a bit of a different form, but we have a lot of similar stuff. Now this one back in the day was set up on a positioner. So they'd use an arm to control the height of this above the steel to be welded. And it wasn't as mobile as ones we have today that we can hold by hand. But a lot of the parts and pieces are all the same. So we've got gas delivery. We have our contact tube, our contact tip. We got our liner at the back. We got our drive rolls in the middle and our roll of wire at the top. So it's very similar to the process we use today. In fact, the process we use today is honestly hasn't changed that much. The components have gotten better, smaller, more efficient, but it's all very, very similar as to what it was back in the day. So gas metal arc welding principles of operation. We're going to go over what makes this tick and how it works. So gas metal arc welding is defined as a process that joins metal using a continuously fed wire electrode. So the rolls we use in our class of electrodes are generally about 44 pounds. It's a small thin wire, 0.035 of an inch in diameter. And there's probably miles of it on that roll. I've never done the math to work out how much there exactly is, but it would be a neat project. And I'm going to do that one day. And we're going to use some mathematics. We're going to calculate approximately how much is on a roll of wire. So that's pretty neat. I'll have that number for you one day. It's a lot though, I can tell you that. Atmospheric contamination is prevented by using an externally supplied shielding gas. Now with these welds, when we take part in the welding process, when we create that weld, we actually need to protect it from the air we breathe. The air we breathe is not going to be good for the weld. It's got a lot of nitrogen in it, CO2, oxygen, and oxygen in any amount over a couple % is not good for welds. So what that does is that creates an effect on your weld called porosity. And porosity is going to look like you bit into an aero bar. So an aero bar, as we all know, has a nice smooth outside and full of holes on the inside. That's what our welds are going to look like when we weld without gas. In fact, there's going to be a little bit of bubbling on the outside too, but the whole inside is going to be full of voids and hollows, and that weld isn't going to have any strength at all. And that is a bad defect, probably the most common defect we see as welders, and it's the one that we need to know how to avoid. So the power source is direct current electrode positive. That's what DCEP stands for, is direct current electrode positive. It's also known as constant voltage, except when a voltage sensing wire feed is used. So there are multiple different systems that we can use to do this, and we're going to go over them bit by bit. I'm going to try to break it down in a way where it isn't confusing the heck out of you, because there is a lot to go over. So what we're looking at here, folks, is the end of a MIG gun, or a gas metal arc welding gun. So this is the neck right here. I hope you can see my cursor on the screen. This is the neck of the gun, and this is going to be the cup that shields or directs the gas to your work. So we have our steel piece that we're welding on. We have solidified weld metal here with yellow. This red here is going to be our molten weld puddle. Just above that, it's going to be our electric arc. The blue we see in this diagram here is going to be our welding wire. That is what becomes our weld. The green piece here is what transfers electricity from the gun to the wire. So that is a neat process there. Got some people in the shop here. So what I'm going to do is I'm going to put my mic on, or my headphones, and just use my headphone mic. So hopefully you guys can hear me a little better now, a little more clearly. So this setup's quite neat. It's cool. Yeah, everyone thinks it's just a gun, but there's lots of stuff that goes on inside this gun. We have a bunch of different wires, and they all do different things in there. So this teal one here is our current conductor. That is sending the juice to the end of the contact tip. And that juice helps burn off this wire. That's what makes our weld. The solid wire electrodes, the blue. This is our wire that we're actually burning up. Whoops, let's back that up. So this wire becomes our weld. And this kind of fuchsia colored one here is our shielding gas. So that is where our shielding gas, which is in a big bottle, comes down, and it comes out the end of this cup here and covers our weld. It forces this air out around, well, not air, it's a gas mixture. It forces the gas mixture out over top our weld and creates a happy little environment here for a weld to form in. And this keeps our regular atmosphere, everything out of the weld. That weld needs to cool down in an oxygen-free or anaerobic environment. This helps it solidify properly, harden, get the properties we want out of that weld. So there's a whole bunch of stuff going on. This is just a quick breakdown. We're going to move forward in this, and there's going to be some more other diagrams we'll go through that explain it a little better, I think. So the principles of operation. A lot of people call this MIG welding, and that's a term that's been used forever, and there's nothing wrong with it, except in today's time, we're leaning towards calling it gas metal arc welding. MIG is not quite an accurate term because CO2 under the right conditions is not inert. So MIG, metal inert gas, not quite the best term for it. So gas metal arc welding is GMAW. That's what GMAW stands for. In most processes, we use the term MIG because it rolls off the tongue nicely. But CO2 is not inert. I've just been over that. The term gas metal arc welding is more accurate. And the whole reason why we use gas metal arc welding, just the welding process in general, it's quite fast. It's good for production. And if we are manufacturing lots of small parts, it's much more efficient as far as its use of its electrode, which is that core wire, than processes like shielded metal arc welding, which we'll focus on in the next unit. So there are some other things in the semi-automated and automated process. I talked about flux cord arc welding a little bit. So that is very similar to MIG, except the wire composition is different. It's got a different type of wire that we use, a little bit bigger as well. And shielded metal arc welding. Stick welding, you know, it's a process we're going to focus on in the 1050 unit. I'm not going to explore it too far or go into it any more than we need to today. So we have equipment for gas metal arc welding, and this is basically all the components you need to have a, to set up a hard wire welding system. When I say hard wire, I just mean a solid wire like an S6. S6 is going to be completely solid, whereas some other wires are hollow and they have filler in them, and they can be used without a shielding gas. That's the flux core process. So we need a power source, and that's usually constant potential. That's what CP stands for. We need a wire feeder. That wire feeder is basically what drives and pulls the wire off the roll, feeds it out the end of the gun. So we need this to deliver the wire to the end of the gun, so it can be energized by the contact tip and then burnt off into our weld. We need our welding gun and our cable setup. So the welding gun is going to have input controls for the remote, or they call it remote controls, basically just trigger controls. Because you pull a trigger on these guns, it's usually yellow, and that's where you pull the trigger, and that's what tells the motor to start feeding wire. There's a few things that happen when you pull the trigger. We'll get into that in a little bit. You need some filler wire. You need something to weld with. So some material to form a weld with. And you need shielding gas and control equipment. Otherwise, you will be doing a bunch of welding, but it's going to look like doo-doo because you have no shielding gas and our atmosphere's got in there. And we got all sorts of oxygen, CO2, nitrogen up in there. I think our atmosphere is like 71% nitrogen. It's pretty crazy. Oxygen's like 18%. Then the remainder is made of CO2 and some other little things there. But yeah, it's a lot of bad stuff for welds. Basically, that's the long and short of it. So power sources. We usually use DCRP. Now you're going to see a lot of acronyms in here, and they can be quite confusing, and I still even have trouble with them. So if you're a little lost, don't feel bad. So DCRP. So DC simply stands for direct current. No, it's not the shoe company. I know there's a DC shoe company, but this is not what it stands for. So DC, as an electrical term, is direct current. RP is going to stand for reverse polarity. So you'll see RP sometimes and you'll see SP sometimes. They both mean different things. RP is electrode positive. SP is electrode negative. We'll get in further into that. We'll hit those points again as we carry on. power sources include motor-driven generators. So a motor-driven generator is a big gas welder you see on the back of all those trucks heading up to Airdrie or to go to ProPack, or that you see like on pipelines. All those welders are motor-driven generators. This is what I had on the back of my truck when I was working in Fort McMurray. When I was working in a bunch of different sites, I had my own welding setup in my truck, and it was a motor-driven generator. Nice thing is, a motor-driven generator gives you your welding power and also 120 and potentially 240 power. So you can run tools off of that generator and welder. I don't recommend running them both at the same time because it can be a little hard on the motor, but generally if you're welding, you're not grinding. If you're grinding, you're not welding. So you'll pick up one process, set that down, and then start the other process. Transformer rectifiers. That's a type of welding machine where we bring in a low input power and we step it up to a bigger power, a usable power with a transformer. And also we have inverter technology, which does a similar thing on a very small scale. They're light, they're kind of the newer technology ones. Many gas metal arc welding power sources will produce both constant current, so that's what CC stands for, constant current for stick welding, and constant voltage. That's what we usually use for gas metal arc welding process. So here we have a general picture of a gas metal arc welding gun. And what we have is our connector on the back. It's gonna have a few pins. Then we have a positive and negative lead here. Now, some of these guns can be water cooled. In fact, this gun may be water cooled. Looking at it, it's got a sheath and a cover over it. If this gun is designed for high amperage, something like metal core or big flux core, it's most likely going to be water cooled because electrical components and heat don't go well together. I don't know if you guys have ever left your phone out in the sun, but you see it's temperature warning, you know, it'll shut down all functions basically until it cools down. That's to protect its internal components. Same thing has to happen on these guns. We can run a lot of power through these guns. And when we do that, we start heating up components and we start wearing things out. We can start burning up components even, and these guns are not cheap. So some of these guns, like you see here, have these two little hoses on them. It's an inlet and an outlet, and that's going to be for a cooling tank and a water pump. And this will connect to there and it will circulate cool water through the gun, kind of like how a radiator system on a car works. Cool water through and, well, it'll run water through, then it'll cool it in a radiator system and then pump that cooler water back through, maintaining a nice usable temperature for the gun. We don't generally see that as a problem in our shop. We don't run equipment this big, that hot, or this heavy. But out in industry, if you're working in a big steel production facility, you may see something like this. So gun and cable assemblies are rated by their current carrying capacities. We have some examples in the shop here of some very small, light hobby machines that are good for maybe 100 amps. And then we have some big ones that are rated for, you know, 300-400 plus amps. We generally don't run them that high, but you'll notice all the circuitry, all the components are much bigger and heavier. It's kind of like looking at a small quarter-ton pickup and a 1-ton pickup. You're going to notice size differences. Everything's going to be bigger on the 1-ton pickup. And that's simply to help it perform the task better. Same thing applies to these welding gun and the cable assemblies. You don't want to put a great big heavy load in a little quarter-ton truck. It's not going to be well. It's not going to work well. You might break it. Basically, the same thing applies with small welding guns. If you try and run big amperage with a small welding gun, you're going to cook that sucker real quick, and then it's no good for you. Cable assemblies are designed to carry the shielding gas, the current, the wire through a liner, as well as wires for the control mechanisms, such as the trigger. So lots going on in those cables. It's not just a hose and a wire. So the filler wire we have is pretty neat. It's cool technology. Designations. Well, let's go back this up a second. These filler wires, they are classified into two main classifications. AWS is American Welding Society, and the CSA is Canadian Standards Association. So these are the bodies that regulate the production of these filler wires. What happens is these wires get made, then they get tested to a certain standard. AWS has their standards and CSA has their own. You guys have heard me talk about CSA before. It's that green triangle on the steel toe boots. It's the people that test our safety glasses, make sure that everything meets standards before it's sold to the public. Basically, it's, manufacturers make the wire. These companies test it and they say, yep, you're good. You met our standards. Yep, you met our standards. You're good. So it can be sold to then the American and Canadian markets if it has both these designations. So the wire we most commonly use in here, though, is an ER70S6. That is a solid wire. It's copper colored because it has a very, very thin copper coating over the wire. The wire is pretty much all steel, but there's a very, very thin copper coating over the wire to help protect it from corrosion. Because sometimes here in Alberta, we're not too bad, but if I had a roll of bare wire sitting out on a welding machine for, I don't know, a few months, chances are it would start to rust pretty good. We have our seasons here, so spring is a little more humid, it's wet out. Overall, Alberta is pretty dry, but there's still going to be oxidization taking place on that wire. So we coat it in something that's non-ferrous, like copper. Non-ferrous means no iron, and iron is what rusts. Iron rusts red, so that's what is responsible for the rust color we see on rusted steel. So basically, we coat that stuff in our thin coating of copper, and it keeps it from rusting on us. Because sometimes it takes a couple of years to use a roll of wire. Sometimes we go through a roll of wire in a couple months. Either way, we want that wire to be good when we go to use it.
I have a question.
Yes, sir.
I thought copper could also rust and turn like that green color.
It is more of an electrolysis type of thing. It's an electrical reaction. It's not so much a rust. So it's basically, I'd have to look into the science behind it. But as far as I've learned, it's more of a chemical reaction with the elements in the air, not so much an oxidization or rusting process. So,
okay, thank you.
Yeah, no worries. I'll look into that a little more for you, and I'll get back to you on that one because that's actually a really good question. I like that one. So ER70S6 is an imperial designation. So imperial is what the Americans use. Those are our friends down south. We also use it here. Like I mentioned earlier, Americans have a lot of influence over some of the things we do. Like when we talk about our height and our weight, we're feet and pounds, right? We don't talk centimeters and kilograms. In Europe, though, it's, centimeters, kilograms, stuff like that. Even though we are part of the Commonwealth, our American friends in their massive numbers of like 335 million people have a lot of influence on us, and that is one of the things they do. So what you're going to see is in class, I'll call the rod 7018 when I'm welding with welding rod. When we're welding with wire, I'll say ER70S6. That's just how I was raised to say it. In Canada, though, we're metric, so we can also call it ER49S6. The 49, we actually measure the rod or wire strength in megapascals, whereas the United States measures it in thousands of pounds per square inch. So it could be PSI or KSI, could be basically written for a designation for the Americans. And there's a worksheet that we'll work on where we're gonna have to write that stuff down. And no, it's not KSI, that guy. So yeah, claims to be a lot of stuff. A boxer is not one of them. So what we're gonna do is actually, we're gonna back this up just a little bit. Okay, here we go. So a little bit of info on what that number means and how to read it, because right now it probably looks like foreign language to you. But as we get into it, we're going to break it down and hopefully bring a little bit of light to it so you can understand it a bit better. So what we're going to start right here at the top, and we see we've got two designations. We got an S or a T. So S is solid. That means if you cut this in half, it's wire, steel wire the whole way through. And that little bit of copper coating, but yeah, it's steel solid the whole way through. Some of these wires are a T, like a T11, a flux core wire. You could cut it in half, You'd have to pry open the end a bit, but that wire is actually rolled up like a burrito. And inside of that wire is a flux. There is metal filler components. There are gas forming components. There are cleaning agents as well. The flux core is a pretty neat process. And the wire is, yeah, literally like a little burrito. We're going to look at this last, or first digit here. So we got a alphanumeric designation. So we got E. E stands for electrode. It's pretty simple. That's what you pass the electricity through to make the weld. R just stands for rod. Even though this, we call it a wire, technically it's just a really skinny, really long rod that we've decided to wrap up on a spool. So if you see ER, it's just electrode rod, and you'll see that, you know, with like ER 7018. That's a stick welding rod. That's a very common welding rod. This is ER 70S6, which is a very, very common welding wire. We started using some S3 as well, but we're using S6 in our classroom right now. So the 70 stands for 70,000 pounds tensile strength. Could be, you know, PSI, or given that it's 70, I like to say 70 KSI because K is thousands of pounds per square inch. And the last digit here is a code for the deoxidizers in the wire. So the 6, that's the cleaning agents that are basically put into the recipe of the wire when it's made. So when it's doing its thing in the puddle, it's got some cleaning agents in there to help float up the junk and garbage out of the steel. Now, if it's really dirty steel, grimy, covered in oil, mud, whatever it is, galvanizing, those agents aren't going to do it. They're going to, you know, float a little bit of junk out of there, but they are not like a deep scrub agent. They are going to have a fairly clean work piece to work on when you start. So that's why I always talk about prep in class. We got to prep our pieces, get it nice and clean before we start our welding. And that's just to guarantee us the most success. We're going to move to the CSA thing, the Canadian one. Canadian Standards Association is what that stands for. Very similar. ER, we see it here, electrode rod 449. So actually what we do is we measure it in megapascals, and 70,000 equals 490 megapascals. But to leave that, or to put that extra digit in is going to confuse a lot of people. So we drop that 0. So it makes the CSA version a little more confusing, a little clumsy. But once you understand how to read it, it's not bad. But I prefer to use the imperial designation myself. So ER70S6 is what we generally talk about. Yeah, so the top one's AWS. Shielding gases. This is what protects our weld from our atmospheric contamination. Shielding gases can range from argon to helium to CO2 and even oxygen. Now, oxygen sounds crazy, but in small amounts, it does wonderful things for our welds. And when I say small, I mean 2 to 3%. So some of these gases will be just a single gas. If we're using TIG welding, we're using argon for back purging. If we're running a bunch of MIG welding and we want to keep our costs down on gas, we can run straight CO2. Straight CO2 doesn't give us a very nice bead appearance. So what we do is we use a bi-mix, 2 gases on our MIG welders to give us a nice appearance. So what we do is we do a 75-25. We run 75% argon and 25% CO2 mix. So that mix is called C25 or Star Gold. Every manufacturer is going to have their own name for it, but the recipe is pretty much the same. And these are recipes that people have found to work over time, stuck with them, they're tried, tested, and true. So I use C25. That's a 75-25 argon CO2 mix in our shop. Sometimes you get tri-mixes, 3 things, and even quad mixes. And sometimes you will see mainly argon, slight bit of CO2, a little bit of oxygen and some helium in there. Some of these are more specialized. I've never had to do anything like that. Usually the bi-mixes, the C25, is more than adequate. I like it. It's fairly cost effective. As you get fancier with these gases, 3 and 4 items mixed in, cost goes up quite exponentially. Even the C25 can be expensive. I can get straight CO2. I can get a bottle of that for $20 a bottle. The problem with that is CO2 doesn't lend itself to giving you a nice weld finish. So when you're welding and you think you're nailing this really nice weld and you got it, you flip your helmet up, you look at it, it's going to have some rough lines on it. It's going to be gray. It's going to be dull. It's not going to give you good feedback as a student. So I like to use C25. And what that does is it's got a really nice weld appearance, and you buff it, it gets all shiny. It looks great. And when you guys weld, you want to see results. Like, you need to see those results to validate the fact that you are doing well. So working with straight CO2 isn't going to do that. So we use C25, which gives us really nice, pretty welds for a decent cost anyways. Type of shielding gas is primarily dictated by the procedure and secondarily dictated by the cost. One other factor I take into account is, where is this piece going? Firstly, some rules of welding. If you're welding for somebody and you have an engineer drawing and they say this process, this gas, this wire, you must adhere to that. But as welders, we get a lot of choice when it comes to what we're doing. So it's primarily dictated by the procedure. So you're going to need certain gases for certain procedures. If you're doing straight TIG stainless steel, you want pure argon. If you're doing, MIG welding, generally you want the C25, maybe CO2. The cost of CO2 is cheap, but I don't like to use CO2, straight CO2 on stuff I'm publicly displaying. I want my best work out there when people are going to look at it. So I use the C25. If I'm building a bunch of stuff that is going to get hidden somewhere that no one's ever going to see and doesn't necessarily have to look the prettiest, definitely you can buy 3 bottles of CO2 for 1 bottle of C25. It's way more cost effective. So yeah, just think about it that way. CO2 is prominently used because it's cheap. That's why. Okay, so when you get those bottles though, those bottles are sitting about 2,000 PSI, maybe 2,200 PSI sometimes. So a lot of pressure in there. So we need to have a device that takes that big bottle pressure to a working pressure. And that working pressure is what comes out the end of the gun. So that device is called a regulator. That regulator and a flow meter. Well, the regulator basically sets the bottle pressure down to a working pressure, and the flow meter maintains that constant flow of gas out the end of the gun. Some of these are combined, some of these are separate. It really depends on the setup. There's multiple different types of setups, but the ones we have in class are fairly easy to operate. So you're gonna see a hand wheel on the top of the bottle. You're gonna open that up and there's gonna be 2 dials on the regulator and then a hand wheel on there. One will show your bottle pressure, one will show your working pressure. These are quite simple to use, and they're very nice because they hold their position. They don't drift, they don't creep. It's nice. The flow meter side controls the rate of flow. It can be adjusted by the operator and displays flow in liters per minute or cubic feet an hour. So it'll be LPM or CFH. I generally use CFH, and I use 25 CFH as my flow rate for the welding that we do, is 25 cubic feet an hour of gas. Here's a little question for you guys. Flow meters are usually gas specific. Do we know why? There's no wrong answers on this one. So don't be afraid to say something. No one's got anything? All right. So the reason flow meters are gas specific is because gases have different specific gravities. So helium, what do we know about that? It floats balloons, right? Lighter than air. About CO2. A little bit heavier, right? I don't know if you guys ever seen it on YouTube. They'll take a fish tank, they'll fill it up full of CO2, they'll float a paper boat in it. Looks like it's floating. Well, that's because it's contained within that vessel, vessel being the fish tank, and it's displaced the oxygen in there. We suck back a bunch of helium into our lungs, not recommending that you do that, and we get that high-pitched voice, right? Density comes across our vocal cords differently. Then we do what, like, I think it's maybe sulfur hexafluoride, I think, something like that. It's that really deep, dense. You're breathing in something quite heavy. I don't recommend doing this because what's happening is when you're doing this, you're displacing standard oxygen from your lungs. And we need oxygen for our body, respiratory systems, our brain to function, all that stuff. You know, a short little haha, that's kind of funny. Doing it once or twice might be okay, but don't do this stuff long term. You are basically going to be killing off brain cells and damaging yourself. Not something I recommend. Different gases have different specific gravities. That is the answer to that one. So here we have a picture of a flow meter. Pretty simple. So this end here on the right, that goes into the bottle, hooks right up. This screws in, hand wheel gets opened on top of the bottle. This needle goes whoop, up to 2000 plus, saying bottle's full, you're good to go. What happens here is you set the flow rate using this hand wheel. So you turn it clockwise to increase your flow. You turn it counterclockwise to decrease your flow. You need to be in the sweet zone for your flow. Too little, you're getting porosity. Too much, you're getting porosity. That's because there's turbulence coming out of there. So gas is kind of like water. It has to be unobstructed when it flows. So Bow River, normally, pretty good. It flows nice, it's nice and calm. Things are awesome. 2013, great big flood. The river was raging. Water's flipping everywhere. You got white water in a lot of places, big waves, lots of turbulence in that water. Same thing happens to gas when it flows in the air. So if you get the right amount of gas, it just flows nicely and calmly over your well. And if you get a whole bunch too much, it's ripping through there. It's hitting the bits of spatter on the end of your cup. It's swirling. It's not covering your weld fine. And it's getting a bunch of oxygen in there. It's kind of like, you know, people talk about the term whitewater rafting. And what that is the water gets turned up so much, it takes oxygen in. And there's a bunch of oxygen bubbles in the water. That kind of gives it that white effect. That is kind of the same thing that happens as gas. There's gas flowing over your weld, but it's got a bunch of oxygen intermixed with it because we're just flowing too much, too hard, too fast. Then we also have these little flow meters like this one. They're integrated into one deal. And so this is our bottle pressure. It'll tell us how much we have in there. This is our adjustment knob here, and it says how much is coming out the end of our gun. So pretty simple. We can also get these for more than one welding setup. Sometimes people will set up welders where they weld two different things, or they got two different welders, and they'll run them off one bottle because they're both using a process that uses the same gas. So you can independently control these. So you've got one that can come out the left side, one that can come out the right side, and they can be independently controlled via these little hand wheels here. It's kind of cool. Saves us buying extra equipment. When we are welding though, we're getting to some neat metal transfer. And that metal transfer is a cool process. It actually happens in 3 different ways. With this type of welding that we're doing, we're going to stick to one process. And that process is going to be short circuit welding. Short circuit welding is where the wire physically comes out of the gun, makes contact with your weld puddle, it touches. There's an electrical short, it pinches that off when it heats up using the electrical arc, retracts, and then comes forward again and touches that puddle, and it basically touches that puddle a whole bunch of times really quickly, something like 300 times a second. It's very fast. But it has to physically make contact with that puddle to create the short to weld. There are other processes like globular transfer. It basically throws globs of metal across the arc. And that's actually what you're seeing in this little picture here on the front of the screen. You see a glob ready to get tossed off the end of the wire. This is actually the end of the wire. This is the electrical arc or fan. And here's the glob just about ready for touchdown on the base metal. So pretty neat. So we got short circuit, we got globular, and we got spray transfer. Spray transfer is a lot like globular transfer, but instead of big globs of steel across the arc, it's shooting a fine mist of metal across the arc. Hundreds of small individual little droplets of steel. Very, very, very small. So we're gonna talk about short circuit. Maybe the 3 processes and get you out of here for the day, but we'll see where we end up at the end of this one. There's a fair amount to go over, so this will take a day or 2, the slideshow, but we're gonna get through it. So short circuit metal transfer. Here's the process. Drop your helmet, You pull the trigger, you're ready to weld. So the trigger is pulled and the wire makes contact with the base metal. So let's back up a little bit before that. When you pull that trigger, what happens? 3 different things. So that trigger tells the drive motor, all right, I want some wire. Give me wire. That drive motor says, all right, sir, you got it. Starts feeding you wire. Then also at the same time, what happens is it sends a signal to the gas solenoid. It says, hey, I'm going to do some welding. I need some gas to go with it. Gas solenoid says, you got it. Start sending that predetermined amount of gas down the gun to your weld. And then the last thing that happens is we have our, okay, the first one is activates the wire. So wire starts coming up. Second one is the gas starts coming up. Third one is it sends electricity to the end of that contact tip. The end of the contact tip is right at the gun. That's what transfers the power from the machine to the wire. And it says, hey, we need some power down here to burn this off. So that fires up, energizes too. Without those 3 things happening at one time, you don't have a weld. It's kind of like the fire triangle. It needs those 3 elements, fuel, heat, and oxygen to create a fire. Well, this is the welding triangle. You need those 3 things happening to create a weld. So what happens is when that wire comes out there and it touches the steel, makes contact with it, the voltage drops down, the amperage spikes way up there because the machine is trying to maintain this arc. It had this fan going, but when that wire touched the steel, it shut that fan down. So that creates a dead short. So the voltage drops, amperage spikes, that machine's trying to clear that out because it wants to maintain that arc and keep that electricity flowing. What happens is called a pinching effect. This is where it melts a wire off the end, or melts a little glob of steel off the end of the wire via a pinching effect. Once it's pulled that off and it opens up the slightest of little gaps between that ball of steel you just melted off and the end of the wire, that fan, boom, pops right back open again. It goes, yes, all right, amperage starts to drop down, arc voltage pops up, and it's trying to hold that fan all nice. And it does a good job of that. But what happens again is as that wire gets closer to that steel, because it's always continuously feeding, that wire makes contact with the steel again, boom, voltage drops, amperage spikes up there. It says, we got to clear this dead short. Pinching effect happens, pulls that bit of steel off, voltage opens up again because you got that arc, the fan opens up, life is good for a very, very split second again until that wire comes down and touches puddle again. That's basically how it works. It's a neat process. It happens hundreds of times a second. So very, very quick, but this is how it works. The wire is fed faster than the arc can burn it off, and the wire makes contact with the base metal. That creates that dead short we talked about. So that's when the voltage drops, amperage goes way up, says, hey, we need to clear this jam up, and it happens again and again and again and again. So when we get in here, we do some short circuit welding, you'll hear a ripping sound, like an electrical rip. That is that process happening very, very, very quickly. We'll tune our machines. You can tune it by sound. I'll show you how to do that. We'll tune these machines in and you will be able to hear it. And then we'll show demos of what's good and what's not, all that fun stuff. I love doing this. Okay, so if you're into graphs and currents, what happens is current here, no current happening. All of a sudden, boom, we touch down, spiking, we got to burn it off, it starts to clear out. This is all time. Voltage here. Basically, voltage is okay, drops down. We're starting to clear things out, reignition, arc period, all sorts of stuff. But this one here is the one that helps students the most on the bottom. So we got our dead short, starting to do the pinch effect, starting to burn it off. So we have amperage spiking as this is happening here. And amperage is coming up, starting to pull the wire off of the wire, or a little bit of steel off the wire here. This is a wire, this is our base metal, just so you guys know. Here we start to see that pinching effect. The wire starts to get skinny here. It's pulling that little bit of melted wire off there, gets a little thinner, and finally pulls that off the end of the wire. So we have separation again. What we have here is the arc. That little dot is the arc. It's just going to start up as this steel wets out onto the plate. This arc opens up. The arc creates the fan that keeps the metal heated. And all of a sudden we're slamming wire back in here again. We're closing this gap up and we see it here. We got the wire coming down. getting ready to touch, and boom, back to a dead short. Fan gets extinguished, it goes out, voltage drops, amperage spikes to try and burn it off. And this is just a cycle. It repeats, repeats, repeats. So what we can also have in this, basically in the system, are some parameters that aren't good because we manually set our parameters. We tell the machine how we want to weld. We basically create our own welding recipe when it comes to these machines. The recipe is pretty simple. We put in our gas, we put in our gas flow rate, we put in our wire feed speed, how much wire comes out the end of a gun in a minute. Then we put our voltage. The voltage is what helps burn this off. So those are our inputs that we have. So we got a 5-piece recipe, but we need to know how to manage to create these welds. So what can happen is you have too much slope in the workpiece here. And slope is referring to voltage and wire. So in some cases, we can turn that wire feed speed up too much. And instead of having enough power to burn this off, the wire smashes off the workpiece, and it's called stubbing. And it basically just bounces, bounces, bounces. Sounds terrible. It feels terrible on the gun. It looks terrible through a welding helmet. You got chunks of wire breaking, spitting off everywhere. It's not creating that weld you want. On the other side of that, if your wire speed's too low and you've got a very high amperage, what's going to happen is that wire is going to come down, make contact here, and the amperage is basically going to blow this wire up. It's going to basically explode off the end of the gun. And that's not good because it can burn right back to the contact tip, jam that up, no good. When I say explode, it's not an actual explosion, but it's a pop and it just blows that wire apart because we got way too much juice and not near enough wire. So the way to fix that is turn the amperage down or the voltage down or turn your wire speed up. There's 2 ways of fixing those problems. I'll show you that when we get into class. So globular transfer. That sounds like something we're going to get into tomorrow. So talked a lot today, got a lot going on, going through this kind of a little slow, but there's a ton of information here. I want to cover it well for you because there will be quizzes on this. There is stuff coming up, and all this is being recorded, so you have this for reference material. And that's why I'm kind of going through it nice and slow, explaining things a little more in depth. Since I can't have you physically in the class and show you demos, normally I've got a machine out while I'm doing this demo, and I show kids all the effects of different things and stuff like that. But I can't do that. So I'm going through it a little slower today. We're going to basically wrap this up here and stop the recording. So any of you guys